Okay, hello everyone, and I'm going to go ahead and do chapter 1 all in one video. So this video might be sort of long, but I'd rather just do one and do it that way to save some time. Okay, so as the procedure is repeated again and again, the relative frequency tends to approach. That's the law of large numbers. Okay, because you could read about that concept. Okay, the blank for consists of all possible events. That should be the sample space. So the sample space would kind of list every possibility of some random phenomenon. Okay, which one cannot be probability? So probability are restricted to be between 0 and 1. So the middle here is the probability. And what this is saying is the probability can be any number from 0 to 1. So 3 over 5 is 0.6, so that's good. 1's good. Square root of 2 is over 1. So the square root of 2 is bigger than 1. Not equal to, just bigger than. So that can't be a probability. 0 can probability. Negative can't be a probability. Can't be over 1. 5 over 3, check that, that's over 1. 0.01, that's good. That's in between 0 and 1. Okay. Okay, so they're saying it's impossible to get 6 jacks from a shuffled deck, so that would be the probability of 0. That's not 0, that's 0. That's not 0 either. That's 0. Okay, so A is some event. Now, so this would be like all the A's. We'll just draw it. So all the outcomes of our A land here. So then A complement would be anybody over here. So A and A complement share no outcomes. Sort of like an even and odd situation. It seems like it's C here. So pause the video and read through all these. But A and A complement can't share outcomes because that's what the complement means. Okay, so they gave you a probability of A, which basically takes up pretty much everything. So to find the probability of A complement, you could just do 1 minus that. So you put that right in your calculator, and what you should get is, whenever I do my probabilities, I'll definitely do like a 0 first. So I'll do 0.004, not 5, 4. That didn't even go. 0.004. So that's what that should come out to be, 004, and do not round. Okay, 6. Okay, so this is the same idea. They're saying 82% believe that it's morally wrong, and then they're saying does not believe, so it would be 1 minus 0.82, which should come out to be 0.18. So basically it's like what's left over to get you to 1. Okay, 10. So you have 100 of these DVRs, and they're telling you 10 are defective. Now they're saying, what's the probability you pick one and it is defective? So that'd be 10 over 100, because there's 10 defective out of the 100. So that's 10 out of 100, which should be 0.1. So get your calculators if you can't do that, and just put in 10 divided by 100. You should get 0.1. Okay. Refer to the sample. Okay, so you have this table. Now what you want to do is make sure that you get your totals. Let's see if they gave us the total. So what I'm going to do to get the total is I'm going to do 46 plus 11 plus 15 plus 35. And I have my calculator here to figure that out. 46 plus 11 plus 15 plus plus 35. And I get 107. So there was 107 people in all. So they said false positive, so I'm looking to see which one's the false positive. The false positive is the one that's positive. It's a positive test, but it's not right. So the positive, you look at here, up here, positive test result, but it's wrong. That would be these 15 people. So that's 15 people were false positives out of the 107. So I'm going to chuck this in my calculator. 15 divided by 107. And I get 0.10, oh sorry, 1401869. Now I know it says to round to 3 decimals, so I need to round this guy. So I'm coming over to here and see, is this 5 or more? Or I'll just do greater than or equal to 5. That's a no. So then that all just appears and just put in right there. Now I'm going to put the 0 there, but technically you don't need it. So that last 0 I really don't need, but I'll just put there. Okay, so a false positive is somebody who didn't do the drug and their test was positive. So this seems like it would be the person. I think the person would be suspended when in reality does not use drugs. So a false positive is essentially somebody who didn't do it, but the test is saying they did. So they're going to get in trouble when they never did it. So you could just pause that and think about that for a little bit. Okay, so they did this genetics experiment. There was 373 green, and there were 23 yellow. So what I'm going to do is I'm going to add those two numbers up real quick and get the total. 396 total. Let's see what they want to do. They want the probability of a green, so this is your numerator, and that's your denominator. Because you're picking from the 396, and there's 373 to pick from. I'm just going to put this in my calculator. It's 373 over 396, and I get round decimal 3. So 0.9419. So I went to 4 just because this is the one I need to check. Since that's 5 or more, I'm going to change this to a 2. So 0.942. Sorry, I gotta be in the box. Okay, now 0.942, they're gonna start probably ask a question about, is it reasonably close? That's 94%, that's a half. I'd probably say no. It's nowhere near. Okay, so now you have to learn how to set this table up. So we know that there's 500 people. There's 500 people. Now what they're saying is 275 were in a crash. So let me put the 275 down here and let me call this crash up here. I'll just put a yes there. There's 275 last year. So that means that there's the no for the crash would be whoever's left over. So this number would be 225 maybe. So that's 4. Okay, 225 no. Okay, so okay, so they're just talking about one age group, so we don't have to set up a table here. Car crash. We'll be in a car crash. So this should be your numerator and that should be your denominator. 275 over 500. And it looks like it's a 2.5 or a 0.55. And it says round the nearest thousands, which is 3 decimals, by the way. And that's what I got. And it seems like this problem should be more complicated, but it's not. Would it be unlikely? No, it seems like it'd be pretty likely. Would it be unlikely? No. Seems like it'd be pretty likely. 55% chance is a pretty good chance. I mean, I'm going to say, yeah, I don't know what they want here. I'd say, yeah, that's enough to concern me. Okay, so that's 4.1. Okay, let's go 4.2. Okay. Okay, double counting is when you get this situation like this. When you double count, you get a situation and you have overlap. And you count all the outcomes in B, and then if you count all the outcomes of A and you count out all the outcomes of B, you just overcounted the overlap. So you have to be careful. So this would be the addition rule. So addition rule says, you know, add all your A's, that's this circle, that's this circle, and then add the B's, which is like this circle. You can see that middle got added twice. So what we're going to do is subtract out the overlap, and that's your overlap right there. Okay, events that are, let's see, disjoint. If they're disjoint, that means they're not connected. Just to let you know, that means disjoint. There's no overlap. So since there's no overlap, they can't happen at the same time. That's a compound. Compound event is when you're doing 2 or more simple events. The and is the multiplication rule, and the or is the adding. If one does not affect the occurrence of the other one, that means independent. So study that definition. Okay, if your replacement, they will be independent because it didn't mess up your probabilities. The first event did not affect the second one. Okay. I didn't go over this. I talked about this in class a little bit, but there's a rule out there that says you could select without replacement if you take the sample size, which is little n, and multiply it by 10. If you take the sample size and multiply it by 10, and that itself, that product, this product is less than the population size, which we'll call capital N sometimes. So really they selected 1, 2, 3, 5. If you multiply that by 10, that's still less than the 15,958,866. That's the population size, that's the sample size. So if this is true, then you could sample without putting the people back. We still consider them because the sample size, we can still consider them independent, even though it's not independent because you didn't put them back. Okay. Oh, they said no to that. Okay, but because the sample size is not small, that's true. They can be considered independent. Did they replace them or did they not? This is definitely independent. I mean, this is Okay, let's see what this, I mean, okay, so technically they're dependent because it was without, but they're going to probably ask a follow-up to that. But they could be treated as independent. And they have 10%, so they have this as a 5. Different books do different things, but it's going to be good either way. Yes, because the sample size should be less than. So they're dependent, but we could look at them as independent because they take the sample size and multiply it by 5. That has to be less than that number right there, and that's true. Okay, B or C. So to get B or C, we have to add up all the B's. So it's the probability of the B's plus the probability of the C's minus the probability of the A and B's. So I'm gonna add up all the B's. 271 plus 58. So that's 321. So this, or sorry, 329. Now I'm gonna add up all the C. Oh wait, B's and C's. You can't get a B or a C because they have to go to either one. Or B or C or not accurate. Okay, yeah, I guess we can do that. Or not accurate. I'm gonna do this one a different way. We can use the formulas, but it's tricky using formulas when they have 3. Okay, so let's look at the 271. That's B. Let's look at the 58. That's B. Okay, let's look at the 245. That's C. Let's look at the 35. That's C. So these are my B's or C's. Now we need the order. We need the order not accurate. So look at the 36. That's not accurate. So that's good. Okay, how about the 58? The 58's not accurate, but it's already here, so it's already taken care of. We don't need to add it again. Same thing with the 35. Okay, how about I have the 58. Make sure that's 58. Oh, that's from that. Okay, that 36 is taken care of. Now I need to do the 18. This is not accurate. So essentially what I'm doing is I'm just going to each one. I'll show you what I'm doing. 271, 245, 137, 36, 58, 35, and 18. They have to be B or C or not accurate. See, the 337 is not one of those 3 things I said. That's one of those 3. That's B. That's C. 137 doesn't count because that's not one of the 3 things I said. It has to be B, C, or not accurate. Okay, how about the 36? Yep, not accurate. How about the 58? That's B and not accurate. How about 35? Has to be one or more of the things that I said. 35 is C and not accurate. 18, yeah, that's not accurate. So I just add these up and then divide it by the total. So that would be 271. So I got a total of 663. And then were they nice enough to tell us how many there were? Nope. Okay, so I need to add 2 more to what I had added already. I need to add the 337 plus the 137. So in total there was 1137. That's the sum of everybody. So I get 0.583. So 0.583. Okay. So here we have to construct the table. Okay, so to construct the table, so you're going to have negative results, negative or positive. And they said that there were 145 positives Okay, false positive, but this would be no use. This would be use. I'm going to make it look like the other table so I don't confuse you. They had the positive here and the negative here. So 145 in total were positive, in which 29 were false positives. So that leaves the difference, 145 minus the 29, at 116. Okay, the negatives. How many were negative? 151 negatives. There was 2 false negatives. Well, that's a false negative right there. A false negative is a negative that's false. Okay, so if somebody's negative, they shouldn't have done it, but they have the people using it. So this would be 149. Okay, so this is the total here. That's the total here. So now we can get all of our numbers. 145 plus the 151. That gives us 296. That's how many people were there all together. 116 plus 2. That's 118. And then this would be 149 plus 29. That's 178. And if you want to verify, just add these two numbers, which I'll do. I added this and this to make sure I got this. To make sure I got the 296. Okay, now we can answer anything that we want. It's another number of subject. That's 296. How many subjects did not use marijuana? Did not. Okay, here's no use. I got 178. So once you get the table set up, you could go pretty fast. What is the probability of selecting somebody who did not use marijuana? Selected did not use marijuana. No use. Did not use marijuana. It's be that divided by that. So I got my calculator. I'm doing 178 divided by 296. See what I need to round to? 0.601. You just take how many people didn't use over the total. Okay, A or accurate. Okay, so A, they didn't tell us. We already did an order. I'm just going to tell you how to do it. So what you're going to do is do 327 plus 38. These are all your A's. Plus, let's do the accurate. That's 327 plus 261 plus 232 plus 139. These are your accurate. We're going to subtract out the overlap. And if you notice here, that got added and that got added twice. It needs to only be added once, so we're going to subtract that out once. And you're going to take that and you divide by the total. So you do all this and divide by the total, which would be basically everybody. You have to add all of these. That plus 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 that. Okay? That's how you do that. Okay, so the probability of getting made with replacement, they should be independent. Okay, the probability of getting 2 orders from D with replacement. So what's D? So your numerator is going to be 143 plus 10. That's D. You're going to take that and go over the total. The total of all these things. That's D. That's the first pick. Okay? Now you're going to put that people back and you're going to do the same thing over again. 143 plus 10 over the total, which didn't change. That's your second pick. You're going to take these two numbers, these two fractions, and multiply them. And I'll make sure I do another one. Does not affect. Okay, this one I guess I'll do. Okay, so two orders, they're both accurate. So accurate's going to be 315 plus 268 plus 238 plus 144. That's going to be divided by the total. Actually, I'm just going to have you guys do it. I'm going to take that number. Since we put it back, they're both accurate. Assume that it's like with replacements, you're going to do the same thing. Since you replaced it, it didn't change it. There's still 315 of those. There's 268. There's still 238. There's still 144. And the total is still whatever it was. Okay, you take those numbers and multiply. Okay. Okay, so the probability of fails is 0.134. Flip everything to decimals. Okay, so on any one day, the probability of fails is what they gave us, which is 0.134. But if they have two alarm clocks, you just take this number and multiply it by itself. That's the first one has to go off, and then this one has to go off. So I'm just going to do 0.134 and square it. 0.01. Okay, we need to go 5 decimals. So 7.956. So that's 1, 2, 3, 4, 5. So that 5 needs to go to a 6. That's 5 decimals. If they have 3 alarm clocks and they didn't get awake, that means all 3 of them did not go off. So it's 0.134. That's the first one, times another 0.134, times another 0.134. So if he has 3 alarm clocks like that, and he doesn't get awakened, then all 3 of them didn't go off. So it's 0.134 to the 3rd power. And this gave me, I'm going to write this down, 0.002406104. And they want us to round to 5. So 1, 2, 3, 4, 5. So that needs to be a 1. And this will go away. That's a 1. So 0.00241. Oh, I keep doing that. 0.00241. Okay. Okay, greatly improved. So we went from 2%. Okay, no more. I'm going to go with that. It might be wrong, but. Because Toma would not be impossible, but it would be unlikely. Okay. So what they're saying is if you look at like this result compared to like whatever this was, this is somewhere in the 2% range, where this is like the 2 in 1,000 range. Okay. Okay, so whenever you see this thing, probability with the B with the slash and an A, what this means is this is given. We know this already. That we know A's happen. Now we don't know the B. So it's the probability of B given A's happen. Okay, and they say, I'm going to put the words in here. So A is they're telling the truth. And B indicates they're lying. So this is what the test is saying. This is what the truth is. This means they're telling the truth. So it should be, what's a chance that you're going to get a positive result if the person's telling the truth? That would be a mistake. If the person's telling the truth, the test shouldn't give a positive result. Or I'll word it a little differently. So what's the probability the test says lie? The test says that the person's lying when the person's actually telling the truth. That's what this is saying. Looks like the first one. So you guys could pause the video and look. Okay, now find the probability of the student spent given that the student is given 4 quarters. Okay, so I'm going to add all these numbers up to figure out how many you have in total. So 4 quarters, they're given $1. That this was the gum, yes, and this is they kept it. So this is they spent. That's they kept the money. Okay, so 28, 19, 17, and 31. Okay, so I'm just adding to get my totals up. 21 plus 19. This is how many people were given 4 quarters. 17 plus 31. This is how many people were given $1. Okay, 28 plus 17. 45. This is how many people purchased gum. And 19 plus 31. This is how many people kept the money. So it looks like there's 95 people in all. Now the first set question says, okay, what's the probability that they spent the money given they were given 4 quarters? So what's the probability they spent the money given their 4 quarters? So we know that they were given 4 quarters. So the 4 quarters was 47. It was 47 people who received 4 quarters. Out of those 47 people, how many people spent? Spent would be 28. So it would be 28 divided by 47. Once you get this concept, it's actually very logical. So I got, that's going to round. So this is what I ended up getting. And this will happen from time to time. Okay, so it's saying round to 3. Okay, now that's easy. So if it runs to 3, then that 7 is going to turn that into a 6. So 0.596. Okay, find the probability that the student was given the money. So I'm doing this one up here. Okay, they kept it. They kept the money given the fact that the person had 4 quarters. So same thing, 47, and they kept the money. This would just be like the opposite. This is everybody else. So that's 19 over, this is 19 over the 47. This is like everybody else. It's like the opposite of what we just did. They want 3 decimals, so 0.404. Which is the complement of what we just did. Okay, so what does these results say? So basically what they're saying is if you're given 4 quarters, you are way more likely to, or you're pretty likely to spend the money. I'm going to say that. Definitely not D. Well, we never figured this other one out. They were given the $1. A student given 4 quarters is more likely to spend the money than given $1. We never found the $1, but it might be C. Nope, there we go. Okay, So let's go on to the next one. I like when they give the totals for us. They're not giving the totals for us. So what they're saying, find the probability if somebody tests negative, so that's a negative test result, given that he or she did not have the disease. So they do not have the disease. So we have to figure out how many don't have the disease, and that's going to go in your denominator. Okay, the individual has the disease, yes, no. So there's 140 plus 28. So that's 140, 150, 160, 168 people don't have the disease. Okay, so out of these 168, how many were negative? 140. Test negative, given they don't have it. That should be high. They should be tested negative if they don't have it. So I got 0.833333. So there's pretty much an 83.33 chance that they don't have it. What? Something's wrong. I got a number wrong here. Okay. One individual Oh, I went too many decimals. Dummy. I went 4 decimals. Oh. I knew my work was right. I'm sure that happens to you guys. Okay, let's do this next one. What's the probability that the subject lied given the test yielded a positive result? So what we have to do is we have to find out, well, how many were positive results? This would be 43 plus 17 were positives. And how many out of these two groups, that's a group and that's a group, that were added together, one of these were positive. And that would be the 17. So I'm just doing this, and I got 0.283. Okay, round to 3 decimals. Okay, I did that right. Let me just make sure I got it right. That is, find the probability that the subject lied given that the test yields a positive result. So positive results of those two, oh, that should be 43. I went to the did not lie. So it's the complement to that. So it should be 717. The complement of at least one is none. Make sure you know that. Oh, we're going to do some at least ones. Okay. At least ones could be tricky. So, the probability of having a boy on any one birth is 0.531. So here's the rule. The probability of getting at least one, we just did that. It's 1 minus the probability, the complement of that is none. Okay, so the probability at least get one girl. So I'm going to write girl here. This could be kind of tricky. So the boy's 0.531, the girl is 0.469. Now they're saying, what's the probability of getting at least one girl? And how many kids? Among the next 8. Yikes. 8 tries. This would be 1 minus the probability of getting no girls. So this is 1 minus, it would be this to the 8th power. to the 8th power. You could actually do this as a binomial too. We learned binomial in chapter 5.2, but it's a little tricky. So I'm going to work on the right side first. So I'm finding this 0.531. I hit the little caret, raise it to the 8th power. So I have 0.531 in my calculator, raised to the 8th power. Okay, and then I got that, and I do 1 minus that value. It should be a really big number. So I got 0.99. They want me to go to 3 decimals, so that's going to round up to a 4. Now your numbers are going to be different, but you have to use the same logic. Okay, the probability that they fail is 0.1. So the probability they're okay, I'm just writing this, is 0.9. So it sounds like you have 2 hard drives, and we need to avoid catastrophes, so the probability, okay, what can I, at least 1 working, so at least 1 working would be 1 minus they both break. Okay, the chance they both fail is 0.1 times 0.1, so that's the chance they both fail. So I'm going to do the same thing. I'm going to work on the other side, do 0.1 squared. That's both failing, so this should be 0.99. I do 1 minus that, so doing 1 minus 0.01, which came out to be 0.99. So there's a 99% chance that we make it through. Making it through means that one breaks, the other one works, or the first one works, the second one breaks, or they both work. Okay, now with 3, you do the same exact thing, but this is going to be to the 3rd power. And I could use parentheses here or brackets, it doesn't really matter. So this should be 0.999. I did 0.1 to the 3rd power, and then 1 minus that. So I got 0.999. Okay, so that's chapter 4.3. Let's go to chapter 4.4. And this will be our last section. Okay, only 8, good. Start fresh. Okay, in horse racing, a trifecta, blah, 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 combination or permutation. So a horse race would say something like the first 3 finishers. So if this is first, second, and third, and let's say, so this is first place, second place, third place. And let's say the 8th came in first, let's say the 10th came in that, and let's say the 3rd came in third. If you change the order, that's a different arrangement. So this is a perm. Because the order of the first different, it does make a difference. The trifecta is a permutation. And somebody ever gave me the option of, you have to pick the first 3 in that order or not in any order, I would definitely not pick that choice. Okay, if the order of the items matters, that's a permutation. Okay, so there's a state lottery. So we could pick numbers from 0 to 9. Oh, I know what happened. I just have to get this a little shorter. Okay, good. Any selected number can be used more than once. It shouldn't be a perm or a combination because you're allowed to replace. Okay, so combination and permutation are only allowed if you don't replace. And it should be multiplication, not factorial. Because you're going to pick 4. Now, if you were going to pick 9 numbers, then it would be the factorial. So to be a perm or a comb, I don't know what that is. Oh, it's a thing. Okay, so there's 8 keypads. So it'd be something like you have 8 numbers to pick from. So let's just make them up. 1, 2, 3, 4, 5, 6. So that's your keypad. Repetition is allowed, and you're picking 4 numbers. So what you want to do is on your first pick, you have 8 choices. Since repetition is allowed, you still have 8 choices. So this is going to be 8 to the 4th power. This is called the counting rule. So there'd be 8 times 8 times 8 times 8. It's easier just to do 8 to the 4th. 4,096. So to pick that would be, so I got 4,096 was this. To choose it, then your first pick would be 1 out of that number. So I don't really know. So I could do this, see if this works. Oh, I hate this cable problem. Okay, so we're testing the current color coded. So there's 5 wires. So that's the first wire. Let me make them a little thicker. That's the first wire. Second wire. The third wire. That didn't work. It's the 4th wire. That's the 5th wire. Okay, how many tests are required for each possible pairing? So I'm going to go back to here, back to that color. So that would be like 1 pairing. Now the question is, if you change the order of these pairings, does it become a different test or is it the same test? See, this would be like a different pairing. You know, basically that'd be like 1. That's like 2. That's like 3. That's like 4, 5, 6, 7, 8, 9, 10. I'm pretty sure there's only 10. Because what happens is, just think about it conceptually. If you pick these 2 right here, say you pick those 2 and you do that test, and you flip the color of the order, you change the order of the color, does that require a different test, or did you already test those 2 colors? And the answer to that should be, that shouldn't count as 2 tests, that should count only as 1 test. So in this case, you should have a comb. You should have a comb with 5, and you're picking 2. Okay? This is a refresher. You want to do you want to go to StatCrunch and go to data, down to compute, expression, then you'll hit comb, C-O-M-B, with an open parentheses, and you're going to hit 5 for how many wires you had, and 2. I'm pretty sure this should hit compute and it should pop up there at 10, which is kind of what I had. Oh, where'd my stuff go? Hey, my thing went away. Sorry, I know it's already a long time already, so. Okay. Okay, so that's the same thing, but every pair. Well, that's 5 wires at a time. I don't know. I mean, it's a different word. It's a different worded question. So, you see how to do the last one. That should have been 10. Okay, for a small private school, 6 students are split in from 11. Okay, so the 6th youngest is one group out of those 11. The 6th youngest, say that again. The 6th youngest, there's 11 people. 1, 2, 3, all the way to 11. The 6th youngest is one group. We have to figure out how many groups there are. This is a comb. This is a comb. There's 11 people in your sig. There's 6 people in a group. We have to figure out how many groups there are. If you change the order of one group, that shouldn't count as 2 different combinations. It should only count as one combination. So we're going to do, that's one group out of how many groups, and it's going to be this comb thing. Okay? It's going to be this comb. So you need to go and do that part that I just told you on the calculator. I lost it when I did it. I don't know why, so I'm going to do it on my calculator, which is a little different than your calculator, than StackRhymes. So I'll be there in a sec. Go home. Put a parentheses at the end. So I got 462. There's 462 different arrangements. And those 6 youngest are one of those arrangements. Okay, how about going from different routes? Seven sites. Site 1, Site 2, Site 3, Site 4, Site 5, Site 6, Site 7. Okay, we don't know the length of the routes, but so basically they're saying like how many routes are there? So you're going to take however many routes. This is the total number of routes. And to get the shortest one, there's one shortest one out of all those routes. So like for example, if they want in this order, 1 to 2 to 3 to 4 to 5 to 6 to 7, that's one route out of how many? So we have to figure out how many routes there are. This might be the shortest one. There's one shortest route. We don't know what that route is, but the chance you're going to get it is 1 out of however many you have. Now this is a factorial problem, because when they're making their choice, this is the first random pick. So you have to decide, well, how many choices are there? There's 7 choices. So now on your second pick, let's say that's picked. They're going to 2 first. Now there's 6 choices. Say they pick that. Now they're on their third pick. They're going to go to 1 there. This is just another 1. Now they're on their fourth. 1's gone. They're going to go to, 6 is gone. So that should be a 5, by the way. 4. These represent how many picks they have left. So it's 7 factorial. That's how many routes there are. There's 7 factorial routes. One of those is the fastest route, so we do a fraction. So it's going to be 1 divided by whatever 7 factorial is, which is 7 times 6 times 5 times 4 times 3 times 2 times 1, which comes up to be 5040. So it's 5,040 different routes, and the chance you're going to pick the shortest is 1 out of that. How many different ways can offer be? Okay, so we have a CEO, a COO, and a CFO. Now, how many people are going to be going for this job? Okay, there's 12. Oh, there's 4 jobs, and a CFO, COO. Okay, president. I forgot the president. So there are 4 potential jobs, and there are 12 people. So see how you're picking 4 out of 12? That's what makes it either a comb or a perm. Okay, so whenever you're picking a portion out of the whole, you can still do counting rule if it follows the perm. So in this case, this is going to be a perm because order actually makes a difference. Because there's 12 qualified candidates. So if you make candidate A for that one, okay, then candidate A is gone. He's already got to put in a job. And let's say that's candidate D, or let's use numbers because there's 11 of them. So let's say candidate 5 got the president. Candidate 10 got CEO. Candidate 2 got COO. And candidate 12 got CFO. If you had said, 10 got president, 5 got CEO, 12 got COO, and 2 got CFO, it's the same 4 people, but they're in different order. So that's what makes it a perm. So you need to go type perm in to the whole data compute thing, data expression compute. And then it needs to be, there's 12 people and they're going for 4 jobs. And that'll get you the answer. Okay, so I want to go 12. And it says there are how many different ways to appoint officers? That's what we're finding. I'm just doing it on my calculator, so it's a little different than StatCrunch. But I showed you how to do it with combs. It's the same thing, but you have a PR, you put this in that same spot, and it'll tell you. 11,880. Okay, so a committee of 4 people. A committee, it'd be like something like, okay, 5's in the committee, 1's in the committee, 10's in the committee, 11's in the committee. So that's one way to have a committee. Well, what if it was 10, 1, 5, and 11? Is that a different committee or the same committee? That's the same committee. So it's not a different committee. That's what makes this a comb. So we have a comb, 12 people, and 4. So go to StatCrunch, how I want the StatCrunch, and then you could do it that same way. Should be way less, 495. So when order does not matter, it's way less. Okay, getting the 4 youngest of the 4 qualified candidates. So out of these 1 through 11, let's say like 1's really young, 4's really young, and 9's really young, and 11's really young. Okay, so let's say these are your 4 youngest candidates. Now what's the chance of getting these 4 candidates? Okay, this one's kind of a little bit tricky. This one is a little tricky because the problem is if you change the order, that would actually matter. So this should be 1 over this top number there. I'm going to do it in fraction. 1 divided by 11880. Pretty sure this should be right. Okay, so Let me try something else. Okay, now this one is a little tricky. I won't give this one, but I'm just thinking about it like this. I'm going to do this 4 factorial over the 11880 and see if this works. Because my thought process was, if they get the 4 youngest, let's say 1's the president, and 4 is the COO, whatever. 9, he has a job, and 11 has a job. This is why this wasn't right. What I just did, I did 1. So what I did was, this would be the chance that these 4 people got the job in that order, in this order. We have to figure out, like, well, how many different orders can these 4 people go in? Like, it could have been 11. It could have been 4. Okay, so then this should just be, this denominator is wrong. Okay, I got another shot after this, so this will also give you the same answer too. I'm pretty sure that 4 factorial over this will give you the same answer, but I'm thinking that we could do this as a combination and do 1 over 495. Pretty sure this will work. Okay, and go back and listen to kind of like my thought process. My initial way that I did it was definitely not right, because 1 over 11880 would be saying that the 4 youngest got it in that order, like Pres, COO, CFO, CEO, something like that. Would have to be in that same order. So, all right, that's additive 8. So that should get you mostly through chapter 4, and hopefully it was helpful.